So we're going to consider various colorings today. I took more or less by random several colorings which I don't work on, and maybe one or two colorings that I work on. And I could took some other colorings, but I just by random decide this one. So it was not something like I feel that this kind of coloring, if I mention it, it should be very important. Just and that I should speak about it. But it was something like let's choose several ones. Yes. So the first one I choose it is, of course, at the beginning I choose older one and then later newer one. Yes. Acyclic coloring. Do we know what's mean acyclic coloring? Do anybody ever work at home, read it something about acyclic coloring? Do you know how we define acyclic coloring? Nobody ever heard anything? You know?
So what is acyclic coloring?
Sorry?
Acyclic coloring means you pick any two color classes.
Yeah.
And that is obviously a bipartite graph. In acyclic coloring, that should be a forest.
Yeah. Yes, that is correct.
So, acyclic graph, usually the name of the coloring tells a lot about what's going on for the coloring. So acyclic means, as he nicely explained it, in any proper coloring, if we take two colors like green and brown, then of course every color class is independent set. In a proper coloring, we're going to have here all the edges between these two. It looks like this, yeah. There will not be edge here, yes, and not edge here. This is like not allowed it. This is not allowed it because the coloring is proper. So in acyclic coloring, we are not satisfied with bipartite graph. We want to be forest. This should be forest. So whenever we take any two colors, we will not have a cycle inside. Alternatively, we can say on every cycle we have at least how many colors? At least colors, yes. So let me write this a little bit in union of two colors of any two colors give forest, which is equivalent to the stating that every cycle has at least three colors. Okay, and we just like say like this, and let's mention a few results. Yes, what is known. Yes, it is denoted by this way, with A inside down. So it was define it by Branco-Grunbaum. Okay, in 1973. Most of the people were not born then here. So this coloring is older than you. What is known? He proved it. What is known? If delta is For graph of maximum degree 3, we can do it with 4 colors. Then, that was by Grunbaum. Then it was proved later at most 5 for delta is 4. Kostochka and Bernstein. Grunbaum. Okay. Erdős proved it ski of G that there exist graphs for which this is bigger than delta 4/3 minus epsilon. So we will not be able in long run, we will not be able to keep like delta. This is, you see, this is delta plus 1, yes? This is delta plus 1, 3, 4, 5, delta plus 1. And Erdős proved that exists graphs such that it is like delta on power 4/3. This is much bigger than linear bound, yes? So that will not be linear bound. This tells very nicely that we cannot proceed like this in long run. And then Borodin made one very famous result. What do you think? What will be for the planar graphs? This is a famous theorem. Every planar graph is acyclically typos. Five colorable. So if we have planar graphs, we can acyclically color it with just 5 colors. The proof is involved, it's not simple, it's difficult. And maybe 20 pages, maybe even more. I think it used discharging. Borodin usually prove everything with discharging, yes. But sometimes he proves some very strong results, yes. Okay. And here's one conjecture that I'm interested. And your job is to find some information about it until afternoon. Okay? It's not funny. So the conjecture says this. It's about acyclic coloring. Acyclic edge coloring and it was created a long time ago by Fiamchik. Every graph G of maximum degree delta satisfies So we speak about chromatic index, acyclic chromatic index. Yeah, this is I didn't define it now, but I tell you now, this is the acyclic chromatic index, not number, index. So we don't we color here the edges. Obviously, it must be at least delta, probably delta plus 1, it's obvious. So everything is shifted for 1. Weezing says delta plus 1 for usual coloring, delta plus 1. Here will be like mostly delta plus 1, delta plus 2, maybe also delta if the graph has big and very small vertices in such exceptions, yes. But anyway, I'm interested, is it true for delta equal to 3? It's your job to find it. For delta equal to 3, for delta equal to 4, what is known? Maybe it's not known delta plus 2, maybe it's known delta plus 4 or delta plus 3. You have mobiles? You have on mobiles internet, yes? You can check it, yes? Now or later, whatever. I expect afternoon somebody will come and report what you can collaborate together, like search together. And then come out with some small report, what is known about this conjecture. So let's say the smallest, the easiest non-trivial case will be delta equal to 3. Easiest non-trivial. Delta equal to 2 is trivial. Nothing to prove. For delta equal to 3, is it known or is not known? And in general, maybe some weaker bound like delta plus 5, is it maybe known for this conjecture, which is also very interesting to have result, delta plus constant? Maybe delta plus million is true? Anybody see how we prove like delta plus million? Okay, we don't know delta plus million. What about 2 delta? 3 delta? Can we prove like not delta plus constant, but constant grad delta? And what will be that constant, smallest we can do? Sorry? Okay. Let's move to the next coloring. So I want you to report me afternoon about this conjecture. It will be one of exercises. You can use on the telephone search, on the computer search, whatever. Now somebody said is interested in the total coloring. You're working total coloring. So what you proved so far? Do you have any results? If you don't have results, doesn't count. I'm joking. Of course count. Yes, you're young. You're just starting working. I'm just making. Okay, the second coloring, which is also classical, even more popular, is total coloring. Can somebody tell me what is total coloring? You know, yes. Let's see others. Anybody beside her knows what is total coloring? What? Yes. So what is the condition? Anybody else who's aware of this? So two vertices or edges mixing the adjacent incident in color. So one remark for you. Is anybody who is doing here square coloring? You doing square coloring? Yeah, who is doing square coloring or something? Anybody else do some other coloring? No, nobody else doing coloring. So my advice is you cannot just do total coloring. And you do total coloring and you notice if you do, maybe you are focusing the moment on one coloring. You have to read also other colorings, see what's happening there. Let's try what's happening there to adapt maybe to work also here. So you cannot work on one coloring. Maybe the moment on one coloring you can work, but you have to follow many other colorings. And then you see, oh, this is similar to that one. Maybe I can do in total coloring what some other coloring is done or vice versa. So it's not possible to work on one coloring. You should work on 10, 20. Okay? That's my advice to you. Okay? So total coloring is that true. For any incident or adjacent x and y from union of v require that coloring of x is different from coloring of y. So let's see what is the simplest example. Non-trivial. Let's say we have at least one cycle. So if you take triangle, so we have to color the three edges and the three vertices. So we can put color maybe here 1. We must put here to the edges 2 and 3. What do you propose we put here? 3. We put here 2 and we put here 1. So we color the triangle, totally color the triangle with 3 colors. A chromatic number is denoted by this double, what is this, prime, how is called this? Double dash. Okay, double dash. Of G is, of C3, sorry. Of C3. Now, you are facing new coloring like this one. What question comes to your mind, in your mind? You tell me.
Why did we need to learn total coloring?
Sorry?
Why did we need to learn total coloring?
Anybody can answer? So, I didn't define total coloring. I just choose to present it. So, you have a vertex coloring. Why do we study vertex coloring? Then we have edge coloring. We color edges. And somebody came to brilliant idea. Let's color vertices and edges. This is in practice. Of course, this is useful, yes, so somebody came to this idea, oh, let's color this. What about we color not only vertices and edges, but okay, vertices should be colored in the usual way, two adjustments should be colored differently, edges should be colored differently, if they can. And now we color vertex and edge differently in the vertices and vertex of the edge. This is how the story was going. In somebody's mind, I don't know. This is like invented by Vizik and Begzat. Begzat is from Iran or from somewhere there. It's in the middle way between Europe and India, somewhere there. I think it was Iran, yes. So these people, they are reasoning in this way, and you know what? It's one very practical thing. When you're inventing coloring, it's always easy to prove something. Is it true? Yes. You're the first one who's going to prove, yes. So you prove the easy things. And then what you leave, the harder things for others. So that's why we have so many colorings. So it's always easy to invent new coloring, or let's say after inventing new coloring to make some results, because you're the first one. And depend how many people work it, it's getting the coloring harder and harder. Less and less publication. Each new publication, it will be deeper, involving more tricks, more longer proofs, and so on. This is in practice, yes. So, this is why people listen to coloring. This is not only colors, many other things is going on. Like it's domination, like let's make a domination. We have millions of dominations, yes. It's easiest to take variation of something and to be first to prove these things. It's harder to, like, why you should invent new domination? You can still work on Wissing conjecture. There is a Wissing conjecture about, yes, on domination of Cartesian products. Yes, this is like, it's one difficult question, and after several days you realize maybe it's smarter to invent new domination than working on this. Yes, this is how it works in practice. Yes, so I also invented several colorings, so that happens. If you do professionally all your life colorings, you will eventually also invent some colorings. We motivated something, like we got motivated by this, and we make it odd colorings. Yes, it is normal. Yes. Okay, so this coloring was total was invented by Wissing, and Behzad, I think, is from Iran, independently. Wissing made so many independent conjectures and results. In that time, Russia was isolated, and the Soviet Union, yes, 1965. This is even older than me. So, total coloring can be reduced to vertex coloring. Do we know that how? Total coloring can be reduced to or simulated by vertex coloring. Do we know how? So from the graph, we make total graph. And now vertex colorings of this total graph will be the same like total coloring of the original graph. This is nice property. If you can make it of your coloring to these holds, this is nice property. So what we do here, we do new graph. We take original three vertices, let's change the color. We take the three vertices, and now for every edge we put new vertex. And let's take brown. For every edge we put new vertex. First, we connect two vertices, all two vertices, if they are adjacent in the original graph. In the original, oops. Two edges which were adjacent before, now we yes. And now every edge we connect with its end vertices, actually corresponding vertex of the edge. Yes. And this. Okay?
Can you repeat the last?
Sorry?
Last step.
Last step. This is this edge corresponding like when we have for such incidence, vertex with edge. The brown vertices, they present the edges. Let's denote like this way, maybe it's more clear. X, Y, Z. So we put X, Y, Z. Now this edge is XZ, yeah? And this is XY. And this is ZY. So with blue color, we denote the original edges of the graph. The two vertices were adjacent in the original graph, now will be also adjacent. With the pink color, we denote if two edges share common vertex, then corresponding vertices we connect. So vertex XZ and vertex HXZ here, and the HXY here, they have common vertex X. So with XZ, this is the vertex in the total graph corresponding to the HXZ. This is the vertex that corresponds to the HXY. We connect. And this color, how we call this color in English? This is not yellow, but it's like mustard. Okay, curcuma, turmeric, turmeric. Okay, turmeric color, yeah. Turmeric color, because HX is incident with HXZ, we connect X and XZ here with turmeric color. Okay? This is the total graph of C3. This is the total graph. We denote operation. We can total graph of G. And now we have property or proposition. G is let's say this way, total coloring of G, we can say equal or corresponds to vertex coloring of total of G. Okay? In other words, we can write it like total chromatic number of G is equal to chromatic number of total graph. More precisely, we have this. Do we have some nice conjecture here? Do we know for some nice conjecture? Which one? Tell me. Yes, this is the conjecture of Ising, and so you have 2 hours to solve it during the lunch. Okay. It's a very difficult conjecture, I'm joking. It's a very difficult conjecture. Where I was writing this. Okay, we put here, no, not select. How I put extra page? Here, like at page. No, I won't. At page. Let's put some more at page. So here is this famous conjecture, which is like very difficult. if you want to prove exact bound, yes. Total coloring conjecture is known. Total chromatic number is at most delta chromatic, delta degree plus 2.
Sorry? In 2020, there is a person called T. Srinivasamurthy.
It's a Indian guy, yes?
Some Indian guy. He has like he printed a paper saying that he has given a proof for total coloring conjecture. He proved it. Like, there is a proof, but nobody has validated that proof yet. There is a
He proved it in Indian language, we cannot share that, yes? It's some special Indian language, it is not the Indian language, yes? So it's not going to me, if you put such a big theorem, then you would like to put it on archive or to publish in some good journal. Now, did he do that or not?
I don't know. Does he put it's an archive? Well, in archive you can meet. You can sometimes see many different conjectures solved, but they always have something wrong in the proof, like also cycle double color and so on. So it's
People have solved P equal to NP.
yeah. For example, yeah. So. You put an archive, then you habilitate. Oh, I have paper which should be now accepted soon, yeah, and then you get habilitated, and so
It should be officially published in journal. That means somebody, you can always put something in an archive, which is not completely nonsense because they will not let you. Which looks like, you can always put something that looks like other proof of something, but it should be checked. And if this guy didn't publish in some official journal, then I would say something strange with the proof. At this point, I think maybe something strange with the proof. So, because it's not published yet. I think that the rest of the world will be very happy to see proof of this. I see many problems with all the methods we know how to prove it, so he must invent some new method which maybe other people can use this method to solve some other problems if it's true. So many people are interested in this proof, so people would like to publish. Now, why is not published? We can guess now. Yes? Maybe if I have to bet my money, I will bet that maybe something wrong with the proof. Okay? So there is also, beside this, there is also for multigraph variation of the scheme hypothesis. Can you guess which will be the multigraph variation? Similar like this in Gupta, delta G plus mean G plus 1. Multiplicity plus 1. Now,
one positive result, Kostochka, we mentioned it several times, this Kostochka, this Russian guy who is in the United States now, maybe he's retired now, it's time to be retired, I guess. He proved the Shannon bound. This is a very nice result. Theorem, Kostochka. For every multigraph, G I give you here also homework. Okay? you have a total coloring. You can make least total coloring. These bounds hold or they are conjecture. So, is anybody proof this bound for least total? That's your homework until afternoon. Is anybody working on this X least version of total coloring is bounded by. So Kostochka proved this for usual coloring. Maybe he also proved it later when least colorings become popular. Least variation, least version. So afternoon when we start, I hope you look at and tell me if anybody was doing this or not doing this. This is, look, this conjecture is hard. If I put here least, it will be even harder. Probably is also true. And maybe also here if I put like this. With L is harder. But what is surprising, Kostochka solved this total at most 3/2 delta, this Shannon bound, yes? We proved Shannon bound yesterday, yes? For usual vertex coloring. He proved it for total coloring. There's also Shannon bound for edge coloring. So he make a coloring that color and vertices, and it's a very nice result. Now I wonder, is maybe anybody proof here with L? Total least coloring of the multigraph with so many colors. So every vertex has its own list. Every vertex has its own list, which is of colors, which is of size, let's say 3/2 delta. And can we do it total list coloring? So list may be different, of course, for different vertices. That's your homework to afternoon, okay? Try not to solve it, try to look to find it. Is it known? Who was working? What is the best result? And here, I think that Bruce Reed, Morelli, use Bruce Reed. They have some weaker bound delta plus 2 for the usual coloring. They use this probabilistic method, second moment, Chernow bound, Azuma, blah, blah, blah. Try to find what have they proven. Try to find what they have proven. So they have something delta to something f of delta. And this f of delta probably is asymptotically smaller than O of delta. This is small O. And maybe even much better. So try to find what they have it. Muller and Bruce Reed, I think they were working on this. And so they solve many conjecture in this way asymptotically, which is not one, but maybe which delta, function of delta, which is like asymptotically smaller than linear delta, yes. It's like log delta maybe. Maybe they have log delta or something like that, asymptotically. Try to find it, yes. So we have time for one more coloring. Anybody want to introduce some coloring? Now? Variation of total coloring. So what are the variation of total coloring?
There is equitable total coloring.
What?
Equitable.
Equitable. The equitable, I split the edges, the vertices in the same size, yes? Alright?
That is equipartite.
Equipartite. And what is equitable?
If you take any color class.
Do you have to come to the bracket? That's right.
the spelling? Now this is a variation of total coloring. We take it same only. F is a map from union of vertex set from n h set to maybe some 1 up till k. This is the colors used. Now, if we assume that let's see 1 up till ck maybe, n of CI number of times a color CI is used. Like number of times a color CI occurrence. Number of occurrences. Occurrences of CI. Then for any Cij, the absolute value of n of Ci and n of Cj should be less than or equal to 1. That means number of time any two colors have repeated should be, number of times any two colors repeat should be 0 or can differ by at most 1. Suppose if one color is repeated 5 times, then the second one can be 4 or 5, like depending on that. Now there are two conjectures. First one was given in 1994 by a person named, I don't remember the full name, something. This was the first name. So he conjectured that if k is greater than equal to maximum of chi double dash of g and delta g plus 2, then g is k colorable, total colorable. Like total, oh I did not introduce, minimum number of colors for which this condition holds is total equitable coloring, and it is denoted as, actually chi double dash of g is here, chi double dash of g is also denoted as chi t. So here it is chi te. This is the minimum number of colors for which such a coloring can exist. Now g is total. If k is greater than equal to this, then k is total equitable colorable. This is the first conjecture. The second conjecture is, I think, 2002, Wang gave this, that, how to end this? Lot of work has to be done in this area. That is why I was actually looking forward to this. Only cycles, complete graphs. Like if you want an example, best one is C6 or C4 also we can take best example. You give 1, 2, 1, 2, 3, 4. All the color classes are having exactly 2 elements. Number of time 1 appears, number of time 2 appears, 3 appears.
Delta plus 2.
There are two conjectures.
This is much longer than the total color.
If we prove this,
Yeah, implies, yeah? Oh. So, this, you believe in this? How old is this conjecture?
oh, 2002.
2002.
Only very few graphs have been worked on, like planar graphs also, like up to delta is equal to 5, less than or equal to 5. Not much work is done.
So, only few classes of graphs is proven this, right?
Not much work is done. But like simple graphs also, deregular bipartite graphs, like things are not clear. So, if, no, it is not. So not completely. For KMN, it is clear. For KMN, complete bipartite graphs, it is clear. But
Complete bipartite. Okay.
all the other graphs are like little dicey situation. So if somebody wants to take up, can start with one basis. But it is not easy. Also, already snarks are already exhausted in this.
Can you try this? What is known? Cycles, okay?
Let me cycles, complete graphs, complete bipattern graphs will be reduced. Not completely.
So what do you believe this projection or not? I don't believe this. You know, if you improve only for complete bipattern graph, complete graphs, your cycles, but
Cleaner graphs also evident, snarks are evident.
Brian does.
Not in general, some conditions of data, caudal graphs, like what is in that?
All choreographs.
Some conditions.
Some very particular one.
But work has been done that way.
Very optimistic projects. Very strong.
Almost all variations of total coloring have similar code, delta plus 2, delta plus 3.
There are some other variation about total coloring.
Yeah, there is interval total coloring also. I don't know much about it, but the colors that you give.
So you prepare fast enough. You will tell us little bit. Who else is candidate to speak something afternoon? We have like square coloring, yes. Total coloring, some variations. What are you gonna speak? The lady there. You do colorings, yeah?
I was like, all coloring majorly, but I think you are going to.
You know?
I was like,
All coloring. It's loose in this color. Okay, any other coloring we can have afternoon on your side? Cosa tam, che sto con storia? Okay, 1 minute. Can we prove? Do you know the solution for C6, for C5? Can you draw us? For cycles? You don't have to solve, you can try to solve in there. Doesn't matter, come here and demonstrate how you are trying to solve it to others. Come. C5, you don't have to solve it, you can try, yes? C5, C6, to get, maybe for 6-6 it will be again simple. Maybe we can try 6-6, yes? I think C6 is two key colors. We don't use only 4 colors, so 6 4 colors. Okay. She's trying C5, so we try C6. And we try to make to find out what is in general statement for all cycles, full cycles. That's right.
This is total chromatic number.
Need for? As for the projection is delta plus 2, it should be 4, yes. It should be 4, yes. Even for C5, C7, you can do the general, how you go?
Actually, if I'm giving, it actually depends upon some algorithm. I can't remember but for vertex I, if you give 1, 2, 3, 4, some mod 4. So again you start with remaining vertex. If I'm giving 1, 2, then the next color, I plus 1 color I have to give here.
So in the general for cycles, C to K plus 1.
I don't know actually.
C to K plus 1. So imagine you're writing paper. You're writing paper and one of your claims is that every cycle, probably both cycles will separate from your cycle separate. They will be different argument. So you have to make general argument for all cycles, general argument for even cycle. You either you prove it by induction, or you just define it here and you see that this works and somehow explicitly like construct the coloring or
Actually, the thing is ki it depends upon the value of. I am guessing it depends upon the value of cycle. See what it is.
no, we speak about all cycles.
Yeah,
All
if
cycles,
it is,
I guess it's harder.
I
Yes.
can categorize it from there. I think.
I guess all cycle is harder. Yes. Even cycle is easier.
Okay, see.
If I'm not wrong.
Let's see. So interesting. Is it the same? I think there will be two cases. When it is n is 1 mod 4 and then when n is 3 mod 4. So that is,
Okay. Depends what kind of orders we have. 4K plus 1 or 4K plus 3.
I don't remember the.
Okay, yeah, of course, sometimes it happens that usually.
Three, four, 2, 3, 4, 1, 2, 3. And it's appearing 3 times. And then it's appearing 1, 2, 3, 4. 1, 2, 3, 4. And what is 3. Yes, I can provide it. So, cyclically I'm giving vertices 1, 2, 3, 4, again 1, 2, 3, 4, and so on. If it is 5, little manipulation I have to do on the 5th vertex after I finish 4. Because that last vertex after I finish the first 4, next 4, that last vertex I will color like 3 and 4 at next 3 and 4. This is the only variation when n is congruent to 1 mod 4. Otherwise you can repeat almost the same pattern. Then here you can nicely color 1, 2, 3, 4, 1, 2, 3, 4. And if I am giving vertices 1 and 2, the corresponding edge I will give. Suppose if I give I and I plus 1, here I will give I plus 2. 1, 2, then 3, 2, 3, then 4, and so on. Cyclically I am coloring.
So it's called total equitable.
Yes. T-I-T-E. The spelling. Spelling. Table.
Okay. So is it now for Peterson graph? It should be, yes.
Cubic graph is I think already done, exhausted.
All cubic graphs.
The conjecture is true for a cubic graph.
All cubic graphs. Or maximum degree 3. It's not the same.
No, cubic graph it is done, I'm sure. There is a separate paper.
Powers to power vertices except K4, yes. Or we can calculate 1, 2, 3. And if there's a perfect matching, it's called really. So you prepare some more information for afternoon for this equitable coloring program, okay? What is known?
Exam is
What is known? What is not? Are you going to prepare for the exam? Take your great questions. Okay, then we can stop now, yes?
Yeah.
I think, so when you wait to prepare for the, I would rest. Okay, we meet at 2 o'clock, yes? I have to go to prepare. So,
this kind of
mas eu falei, José, morei com isso, mano. Because I know this. I know José. He's military. Morei com isso, mano. She's fast.
these are sufficient perfectly, completely, or almost all possible phase of work. These are certain. This person.
This is something going to
It's a female, I guess.
and she's
So,
so
all her work, like in her career, is like most of her work is only on total relation.
really. This is what I think about.
No, total like all possible ways she was there. Exhausted.
Okay, we are done for today. I must go to prepare something to keep you busy. It's not an easy job for me, but it's my job.
I also see something.
Yeah, try to find something. I guess this will count in your final grade, yes. If you prepare something, this will count. Some plus, extra. 2 o'clock, see you at 2 o'clock. I have to work now.